Question 2 from the 2014 Level 3 Mechanics paper. We're on a pendulum now, and we're given the acceleration due to gravity, and the pendulum is set up in the diagram on the right. The length of the cord attached to the bob is 1.55 meters, so there's our L value. The bob has a mass of 1.80 kilograms. Calculate the time it takes the pendulum bob to swing from one side to the other. Now, one side to the other is half the period, so we have to use half of the equation to find the period of the pendulum, which is 2 pi square root pi upon g. Where do I get pi from? L upon g, excuse me. It's under the square root. So you can see that the 2 and the half are going to cancel, so we're left with half the period equaling pi square root L upon g. We're told the length, we know gravity. Yep, no, that's right. And we could just plug numbers in basically and do that calculation. The next question, oops, that's not my scroll, that's my draw a line tool. There we go. B, explain how the forces acting on the bob change this. How the forces acting on the bob change the bob's speed as it travels from the point of release to the center. So point of release is out to this side, and it swings in roughly that path, but we're only after to the center. So it's this section that we're interested in, and we have to explain how the forces acting on the bob change the bob's speed as it travels from the point of release to the center. So the velocity, no, let's talk with speed because we're trying to use the speed. So speed is going to be 0, that's a 0, at release. Okay, starts off with speed of 0 here, and it's going to have a maximum speed in the center. Okay, so max speed at center. Now, the reason it has max speed at the center is as soon as it goes past the center, it's going to start decreasing in speed because there will be a restoring force. Remember, a restoring force is proportional to the negative of the displacement. As soon as your displacement moves away from the center, the equilibrium position, you have a force acting to bring it back. So as soon as you're past that, you're going to decrease speed because you've got a force acting on it to reduce the momentum, reduce the speed. Okay. In the same way, on the left-hand side, you've got the force acting on it during that period to increase the speed from 0 to the maximum. And it's going to, the force is going to change from max at the end here to 0 there. And I guess we're supposed to make this link as well, that force is proportional to acceleration, F equals ma. So the larger the force, therefore the greater the displacement, therefore the greater the acceleration. So when it gets to the point, okay, we've covered that inside and out really well, I think, at that point. One thing they're probably not expecting you to talk about, but might be worth mentioning, is that the component of the force due to gravity that is pulling it back into the center is going to be decreasing as your pendulum bob goes to the center, so that until you've got nothing. If you remember how that's made up, free body force diagram, you've got this tension force, you've got a force due to gravity, force due to gravity, and the force due to gravity is broken down into two parts. The part that opposes the tension force and the restoring force, and it's a small angle approximation that takes that restoring force and makes it act in a straight line back towards the center, really roughly speaking. Anyway, that force is getting less, so the acceleration is getting less. I don't think they need that level of detail. Moving on. C. The bob is released again in such a way that it swings in a horizontal circular path, conical pendulum, with a radius of 0.290 meters as a conical pendulum. There it says it. By first calculating the size of the angle, theta, that the cord makes for the vertical, show that the tension force on the cord is 18 newtons. Okay, how's that going to work? We've got a force due to gravity there of 1.80 times 9.81. We're going to use that to calculate Fg. Fg is going to be the vertical component, so you've got a vertical and a horizontal component of the tension force And what have we got? In fact, we don't even need that. We've got that 0.290 metres distance there, 1.55 metres there. Use trig to find the angle. I've got a train coming, so I'm going to pause it because it'll be a bit noisy otherwise. Okay, train's gone. Recapping really quickly because my mind's jumped out of the loop. We've got the length, so we've got that side of the triangle. We've got that radius, so we've got that side of the triangle. We can use that to find that angle there. That's going to be a sine theta equals opposite over hypotenuse. Once you have theta, you can then use it in another similar triangle. Well, in fact, there's a similar triangle. There's your angle. You've got the force due to gravity acting down there, which is what we calculated across there, and you use the force due to gravity, that angle theta, to find out what the tension force will be, and you should get an unrounded value which rounds to 18.0 newtons. Okay, part 2 says calculate the speed that the mass must have been given when released in order to attain a horizontal circular path at a radius of 0.290 metres. So we're talking about centripetal force here, and we're talking about that V in there. The centripetal force we can calculate. We've got the tension force, and we've got the presumably the angle. So the horizontal component of that tension force is going to be Fc. The vertical component is the force due to gravity, that is equal and opposite. And so once we use our trig to work out what Fc is, Fc equals trig, we calculate it through the trig, then we've got enough information, the mass was given to us, the radius is given to us, to rearrange for V. So we go V equals Fc R over M, and we have to square root because of that squared factor. We plug in our numbers and we're going to find V that way. Is that the last question? No, that's it for question 2.